The sleeping barber problem. The problem is an analogy that is based upon a barber shop that has one barber chair, and n waiting chairs for the customers. The sleeping barber has conditions to follow. If there is no customer, then the barber sleeps in his own chair. When a customer arrives, he has to wake up the barber. If there are many customers and the barber is cutting a customer's hair, then the remaining customers either wait if there are empty chairs in the waiting room or leave if no chairs are empty. Here is the flowchart. Start. The barber will enter the shop. Sleeping. Since the initial number of the customers is 0, the barber will sleep until a customer came in. Cutting hair. When the customer enters the store, the barber wakes up and cut the hair of the customer. When the barber is currently cutting someone, the customer either wait or leave. When the number of customers turn to 0, the barber will sleep. Going home. When the closing time reach, the barber will go home. Deadlock. This happens when the barber is waiting for the customer and the customer is waiting for the barber. The solution to this problem includes 3 semaphores. First is for the customer, which counts the number of customers present in the waiting room. Second, the barber 0 or 1 is used to tell whether the barber is idle or is working. And the third, mutex, is used to provide the number of available seats and allows them to increase or decrease the number of seats. If there are available seats, the customers will wait or else leave if there are no available seats. Starvation. This happens when the barber serves a customer randomly. The problem will be solved by implementing a queue so that the barber can serve the customers on a first-in, first-out basis. The dining philosopher's problem. It states that there are 5 philosophers sharing a circular table, and they eat and think alternatively. There is a bowl of rice for each of the philosophers and 5 chopsticks. A philosopher needs both the right and left chopstick to eat. A hungry philosopher may only eat if there are both chopsticks available. Otherwise, a philosopher puts down their chopstick and begins thinking again. The dining philosopher is a classic synchronization problem as it demonstrates a large class of concurrency control problems. A solution of the dining philosopher's problem is to use a semaphore to represent a chopstick. A chopstick can be picked up by executing a wait operation on the semaphore and released by executing a signal semaphore. The structure of the chopstick is an array of a semaphore. Initially, each of the elements of the semaphore chopstick 0, 1, 2, 3, and 4 are initialized to 1, as the chopsticks are on the table and not picked up by any of the philosophers. Here is the sample code. First, wait operation is performed on chopsticks array I and chopsticks array I plus 1 modulo 5. This means that the philosopher I has picked up the chopsticks on his sides. Then, the eating function is performed. After that, signal operation is performed on chopsticks array I and chopsticks array I plus 1 modulo 5. This means that the philosopher I has eaten and put down the chopsticks on his sides. Then the philosopher goes back to thinking. The solution makes sure that no 2 neighboring philosophers can eat at the same time. But this solution can lead to a deadlock. This may happen if all the philosophers pick their left chopstick simultaneously. Then none of them can eat, and a deadlock occurs. Some of the ways to avoid deadlock. There should be at most 4 philosophers on the table. An even philosopher should pick the right chopstick and then the left chopstick, while an odd philosopher should pick the left chopstick and then the right chopstick. A philosopher should only be allowed to pick their chopstick if both are available at the same time.